Welcome to our deep dive into the modern periodic table, its structure, anomalies, and future possibilities. Our journey begins in the 18th century when chemists sought to understand the nature of elements and their relationships. Johann Dobereiner was one of the pioneers who identified groups of three elements, or triads, with similar properties, predicting that the middle element's atomic weight was an average of the other two. Then, in 1864, John Newlands proposed the law of octaves, observing that every eighth element. At the heart of the periodic table is the atomic number, which is simply the number of protons in an atom's nucleus. This number determines where each element is placed. As we move across a row, or period, the atomic number increases, and we see patterns in properties like atomic size, which gets smaller. Moving down a column, or group, the size increases. Other properties like ionization energy, which is the energy needed to remove an electron, and electronegativity, which measures how much an atom attracts electrons, also show clear trends. These patterns help us predict how elements behave. The noble gases, located in group 18 of the periodic table, are unique because of their inert nature. This means they rarely react with other elements. Why? Their outer electron shells are completely full, making them incredibly stable. This stability is why we see noble gases used in everyday applications, like neon lights, which create the bright, colorful signs we often see. Helium, another noble gas, is what keeps balloons floating. In the medical field, noble gases like xenon are used in imaging technologies, helping doctors see inside the body without surgery. Their unreactive and stable nature makes them incredibly useful across various industries. Would you like to add more specific examples or simplify further? Not all elements follow the usual rules of the periodic table. Some, like copper and chromium, have unexpected electron arrangements that change how they react and bond with other elements. There are also diagonal relationships, where elements that aren't directly above or below each other share similar properties. These exceptions make the periodic table even more interesting and complex. In the fascinating world of radioactivity, some elements have unstable nuclei. These nuclei release energy and particles as they decay, transforming into different elements over time. This natural process is incredibly useful. In medicine, radioactive isotopes help doctors create detailed images of the body with PET scans. In archaeology, they allow scientists to date ancient artifacts using carbon dating, and in industry, they power tools that measure thickness or density. Radioactivity, though often associated with danger, provides invaluable insights and practical tools across many fields. Below the main body of the periodic table, we find the Lanthanides and actinides. These elements have unique properties that set them apart. The Lanthanides, often called rare earth elements, share similar chemical behaviors and are used in technologies like LED lights and strong magnets. On the other hand, the actinides are known for their radioactivity, with some, like uranium and plutonium, playing a crucial role in nuclear energy production. Together, these groups expand our understanding of the elements and their applications. Would you like to add more details or keep it as is? Isotopes are variations of elements with different numbers of neutrons in their nuclei. While some isotopes are stable, others are radioactive and decay over time. These differences make isotopes incredibly useful. In medicine, radioactive isotopes are key in imaging techniques like PET scans, helping doctors see inside the body. In archaeology, isotopes like carbon-14 are used to determine the age of ancient artifacts through carbon dating. Whether stable or radioactive, isotopes play crucial roles in both science and everyday life. The search for new elements is an ongoing adventure in science. Using powerful tools like particle accelerators, scientists create new elements through nuclear reactions, smashing atomic particles together at incredible speeds. This quest isn't just about adding more names to the periodic table, it's about pushing the boundaries of our knowledge. Every new element helps fill the gaps in our understanding of matter and reveals more about the fundamental building blocks of the universe. As we discover these superheavy elements, we expand the frontiers of chemistry and physics, paving the way for future innovations. Predicting the properties of newly discovered elements requires complex simulations to understand their behavior and stability. A key challenge is the island of stability, where heavier elements may exist for longer periods than previously thought. Scientists are working to uncover these elements, which could lead to breakthroughs in fields like energy, medicine, and materials science. As technology improves, we're on the brink of expanding the periodic table with new elements, opening doors to endless possibilities.